In the Milky Way, entire planetary systems are tearing themselves apart in silence. Gas giants spiral into their stars. Rocky planets collide and vanish. Orbits destabilize. Atmospheres burn away. This isn't rare, this is normal. And against all statistical expectations, our solar system didn't. For 4.6 billion years, nothing catastrophic enough to end us has happened. Jupiter stayed where it formed. Earth's axis remained stable. Our atmosphere held on. The sun burned quietly. That string of non-catastrophes is what's rare. Because planetary systems are easy to make. The universe builds them constantly. What the universe appears much worse at is keeping them stable long enough for anything complex to survive. And by the time we reach the end of this video, you'll understand why most systems fail and why ours somehow didn't. Our solar system is strangely organized. Small rocky planets close to the sun. Massive gas giants far beyond them. A clean separation between the two. It feels natural. It isn't. Most planetary systems we've discovered don't have this structure at all. They have gas giants orbiting closer to their stars than Mercury orbits our sun. They have rocky planets the size of Neptune. They have orbital configurations so chaotic that planets likely collided and destroyed each other millions of years ago. Our arrangement isn't just uncommon. It's a specific outcome that requires a specific formation process. And that process had to go right at every stage for 4.6 billion years. Let's start with what that actually means. About 4.6 billion years ago, a massive cloud of gas and dust collapsed under its own gravity. The sun formed at the center. Around it, a rotating disk of material spread outward. This disk is where planets form. It's called a protoplanetary disk, and every star that has planets went through this phase. But here's what makes ours different. The disk that formed our solar system had the right density. Not too thick, not too sparse. Too much material and planetary formation becomes chaotic. Planets migrate wildly, collide, and get ejected. Too little material and planets never form large enough to hold atmospheres or create stable orbits. We got the density right. The first filter survived. Then there's composition. Our disk had the right mix of elements. Hydrogen and helium dominated, like everywhere else in the universe. But it also contained just enough heavier elements, carbon, silicon, iron, oxygen, to build rocky planets in the inner zone and icy cores for gas giants farther out. That ratio isn't random. Stars that formed earlier in the universe had fewer heavy elements. Stars that formed later sometimes have too many, creating super-dense planets that don't look like anything in our system. We happened to form at the right time in galactic history. Another filter passed, but passing those filters doesn't guarantee success. It just means the system gets to face the next test. And the next test is where most systems fail catastrophically. Jupiter is the largest planet in our solar system. It contains more mass than all the other planets combined. And it sits in the outer solar system, roughly 778 million kilometers from the Sun. That position is critical. In most planetary systems we've discovered, gas giants don't stay where they form. They migrate inward, toward the star. And when a Jupiter-mass planet migrates through the inner solar system, it destroys everything in its path. Rocky planets get ejected into interstellar space, or they spiral into the star, or they collide with the gas giant and disappear. We've found thousands of systems where this happened. They're called hot Jupiters. Gas giants orbiting so close to their stars that their atmospheres are being stripped away by radiation. Their years last days, sometimes hours. These planets didn't form there. They started farther out, like Jupiter. Then something destabilized their orbits, and they fell inward. If Jupiter had migrated inward during our solar system's formation, Earth wouldn't exist, not as a destroyed planet, as a planet that never finished forming. But Jupiter stayed put. Why? Saturn. Saturn formed at roughly the same time as Jupiter, and the two gas giants locked into a gravitational resonance. Their orbits synchronized in a way that prevented further migration. If the timing drifted even slightly, the inner solar system never survives. Too early, and both planets spiral inward together. Too late, and Jupiter migrates first, destabilizing everything. We threaded that needle. Most systems don't. And staying in place wasn't Jupiter's only job. Jupiter doesn't just orbit the Sun. It protects the inner solar system. Its massive gravitational field acts as a shield. Asteroids and comets from the outer reaches of the solar system, beyond Neptune in the Kuiper Belt, get pulled toward the inner planets. Most of them, but Jupiter intercepts them. Its gravity either captures them, turning them into temporary moons before ejecting them back out, or it deflects them entirely, send them into different orbits, away from Earth. Without Jupiter, Earth would be hit by large asteroids far more frequently, not twice as often, orders of magnitude more often. The impact rate would be so high that complex life would face repeated extinction events. Mass die-offs every few million years instead of every few 100 million. Ecosystems would never stabilize long enough for intelligence to evolve. The fossil record would be a graveyard of starts and stops. And here's the disturbing part. The size and position of Jupiter are both critical. Too small, and its gravitational influence isn't strong enough. Too large, and it destabilizes the orbits of the inner planets instead of protecting them. Too close to the Sun, and it would have migrated inward, destroying everything. Too far, and its protective effect weakens to irrelevance. Jupiter sits in a narrow range of mass and distance, where it acts as a cosmic shield without becoming a threat itself. That's not luck. That's a very specific configuration, one that most systems don't have. And even if they do, even if a system has a Jupiter analog in the right place, there's still another constraint, one that almost no one talks about because it sounds too implausible. Earth's moon is massive. Relative to Earth's size, it's the largest moon in the solar system among rocky planets. Mars has 2 tiny captured asteroids. Venus has none. Mercury has none. Our moon likely formed from a catastrophic collision. About 4.5 billion years ago, a Mars-sized object, scientists call it Theia, slammed into the young Earth at a precise angle and speed. Not head-on, not a glancing blow, somewhere in between. Direct impact, both planets destroyed, too shallow. Theia bounces off without ejecting enough material. The collision ejected an enormous cloud of debris into orbit around Earth. That debris coalesced over time, forming the Moon. And the Moon does something critical. It stabilizes Earth's axial tilt. Earth's axis is tilted at about 23.5 degrees relative to its orbital plane. That tilt is why we have seasons. It's also why Earth's climate is stable. Without the Moon, that tilt would wobble wildly. Over millions of years, Earth's axis could shift from almost upright to extremely tilted. Half the planet is baking in constant sunlight, while the other half freezes in permanent darkness. Mars experienced this. Mars has no large moon. Its axial tilt varies between 13 and 60 degrees over hundreds of thousands of years. The climate swings are so extreme that any surface water froze, sublimated, or got buried. The atmosphere thinned. The planet became uninhabitable. Without the moon, instability becomes unavoidable. But the moon does more than just stabilize tilt. It also slows Earth's rotation. When the moon first formed, Earth's day lasted only about 6 hours. The moon was much closer, and its gravitational pull created enormous tides in Earth's oceans and even in the solid crust itself. Over billions of years, those tidal forces transferred rotational energy from Earth to the moon. Earth's rotation slowed. The moon drifted farther away. Our day lengthened to 24 hours. That gradual slowdown was critical. A planet spinning too fast experiences extreme weather. Hurricane-force winds circle the globe constantly. Temperature differences between day and night become severe. Atmospheric circulation becomes chaotic. A slower rotation moderates these extremes. It allows stable weather patterns, predictable seasons, climate zones that persist long enough for ecosystems to adapt. Without the moon's tidal braking, Earth would still be spinning far too quickly for stable climate systems to develop. The atmosphere would be in permanent turbulence. And the moon's distance matters too. Too close, and the tidal forces would be catastrophic. Massive earthquakes, extreme volcanic activity, potential orbital decay. Too far, and the stabilizing effect weakens. The moon sits in a narrow orbital range, where it stabilizes without destroying. But the collision that formed the moon had to happen at the right time, at the right angle, at the right velocity, producing a moon of the right size at the right distance. Every one of those parameters had to fall within a specific range. If any single one had been off, Earth's climate destabilizes. Complex life gets no stable environment to evolve in. That should have been the end. Statistically, it almost always is. But there's an even deeper constraint, one that operates invisibly for billions of years. Our Sun is a G-type main-sequence star, a yellow dwarf. Medium-sized, medium temperature, stable. It's been burning steadily for 4.6 billion years. No massive flares, no extreme variability, just consistent light and heat. That stability is not guaranteed. The most common stars in the universe are red dwarfs, smaller, cooler, longer-lived. They can burn for trillions of years. That sounds ideal for life, more time to evolve. But red dwarfs are violent. They produce massive flares that would strip away a planet's atmosphere if that planet were close enough to be in the habitable zone. And planets around red dwarfs have to orbit very close to stay warm. So close, they become tidally locked. One side always faces the star. The other always faces away. Permanent day, permanent night. Temperature extremes are so severe that atmospheric circulation might not be possible. Our Sun doesn't do that. It's calm, predictable, large enough that Earth can orbit at a distance where it's not tidally locked, stable enough that it hasn't fried our atmosphere. That's another checkpoint, one that eliminates the majority of stars in the galaxy. Earth is geologically active. Its surface is broken into tectonic plates that move, collide, and create new crust. This process recycles carbon between the atmosphere, oceans, and interior. It's a thermostat. If Earth gets too hot, more carbon gets pulled out of the atmosphere, cooling the planet. If Earth gets too cold, volcanic activity releases carbon dioxide, warming it back up. This cycle has kept Earth's temperature stable for billions of years, despite the Sun getting 30% brighter. But plate tectonics isn't automatic. It requires a molten interior. which requires radioactive elements to generate heat. And it requires a planet large enough that it hasn't cooled completely. Mars is too small. Its core cooled. Magnetic field shut down. Tectonic activity stopped. Without volcanism to replenish atmospheric gases, the atmosphere thinned. Surface water disappeared. Venus is roughly Earth's size. But something went wrong. Its carbon cycle broke. Carbon dioxide accumulated. The planet entered a runaway greenhouse. Surface temperature now exceeds 450 degrees Celsius, hot enough to melt lead. Without plate tectonics, Earth loses its climate control system. Carbon accumulates, heat compounds, oceans evaporate. Venus is what happens next. Earth avoided both outcomes. It's large enough to stay geologically active. Its position keeps it warm, but not overheated. And its tectonic system has remained functional for over 4 billion years. That's not one constraint. That's overlapping constraints on size, composition, orbital distance, and internal heat. All of them had to be satisfied simultaneously. If any single one fails, the climate destabilizes, and the margin for error gets smaller with each requirement. Let's summarize what had to happen. A protoplanetary disk had to form with the right density and composition. That disk had to produce a gas giant massive enough to protect the inner system, but not so massive that it destabilized everything. That gas giant had to stay in the outer system instead of migrating inward. A second gas giant had to form at the right time to lock the first one in place. A rocky planet had to form in the habitable zone. That planet had to suffer a collision at exactly the right angle and speed to produce a large moon. That moon had to stabilize the planet's axial tilt. The planet had to be large enough to maintain a molten core and active plate tectonics. It had to retain a magnetic field to protect its atmosphere from solar wind. And all of this had to happen around a stable, medium-sized star that doesn't produce radiation bursts. Each of those is a separate requirement, and they're not independent, they interact. The gas giant migration depends on the formation timing of the second gas giant. The moon's formation depends on the collision happening after Earth's core differentiated but before it cooled. Plate tectonics depend on internal heat, which depends on the planet's size, and composition, which depends on where in the disk it formed. Even if many of these conditions are individually common, requiring all of them simultaneously narrows the number of comparable systems dramatically. The constraints don't add, they multiply. And when you look at what we've found so far, that multiplication becomes impossible to ignore. Since the 1990s, we've discovered over 5,000 exoplanets. To date, we haven't found a planetary system that matches ours in all the ways that appear to matter. We've found rocky planets in habitable zones. Kepler 452b orbits a Sun-like star at roughly the right distance. Proxima Centauri b, in the nearest star system to us, sits in its star's habitable zone. But Proxima Centauri is a red dwarf. Proxima Centauri b is likely tidally locked and bombarded by flares. Kepler 452b star is slightly older and hotter than the Sun. We don't know if it has a large moon. We don't know if it has plate tectonics. We don't know if its system has a protective gas giant in the right position. We can't even confirm it has an atmosphere. The problem is detection. Current methods excel at finding large planets close to their stars. Hot Jupiters are easy. Rocky planets in year-long orbits around Sun-like stars are incredibly difficult. And detecting moons, measuring axial tilt stability, or confirming plate tectonic activity on distant worlds remains beyond our current capabilities. We're looking through a keyhole and trying to map an entire building. We've found super-Earths rocky planets larger than Earth, but smaller than Neptune. Thousands of them, but most orbit far too close to their stars. Surfaces hot enough to vaporize rock. We've found gas giants everywhere. Most of them are hot Jupiters. The ones that aren't are often in eccentric orbits, sweeping through their systems and destabilizing everything else. We've found planetary systems with multiple gas giants, but they're usually in configurations that would make stable inner rocky planets impossible. The more we look, the more we find systems that don't resemble ours. That doesn't mean solar systems like ours don't exist. We've only examined a tiny fraction of the galaxy. Our detection methods are biased toward finding large planets close to their stars. Those are the easiest to detect. But what it does mean is that systems like ours are not common, and every additional constraint we discover makes them rarer. So here's the answer. Our solar system isn't impossible, but it required a specific sequence of events, each with low individual probability, all happening in the right order, without catastrophic failure, over billions of years. The right star, the right disk, the right formation timing, the right migration behavior, the right collision, the right size and composition, the right magnetic field, the right distance. Every one of those is a filter, and filters compound. The universe appears very good at creating planets. It may be much worse at keeping them stable long enough for anything complex to emerge. Scientists estimate that perhaps only a fraction of a percent of all planetary systems in the galaxy are truly comparable to ours. With 400 billion stars, that would still leave millions of candidates. But millions out of 400 billion isn't common. It's statistically marginal. And we haven't even addressed the hardest question. How many of those systems, even if they pass every structural filter, actually produce complex life? Because Earth didn't just form correctly, it stayed stable for 4 billion years, while life evolved from single-celled organisms to multicellular creatures, to animals capable of looking up at the sky and asking if they're alone. There were mass extinctions, ice ages, asteroid impacts, volcanic eruptions, events that brought life to the brink of total collapse. And each time, it recovered, adapted, continued. Whether that recovery was inevitable or extraordinarily lucky, we don't know. But what we do know is this. A planet like Earth isn't just a rocky world at the right distance from the right star. It's the end result of an improbable history, a history in which countless things could have gone wrong at every stage, and didn't. The solar system that made your life possible isn't the norm in our universe, it's an exception. To date, we haven't found another system that comes close to matching ours in all the ways that matter. We have candidates, planets in habitable zones around sun-like stars, but only in a few aspects. The full package remains unmatched. Most stars may never produce a planet that stays stable long enough for anything complex to survive. And when you understand that, Earth's pale blue dot shining into the void seems less like one of many and more like an outcome that shouldn't exist as often as it apparently doesn't. Not because someone told you it was special, because now you understand how easily none of this happens.